going hand in hand with our inductive and deductive reasoning and the idea of these proofs is logic. So we're going to talk real briefly here about logic and logical statements. So when we talk about a mathematical statement, it's something that can be either true or false, but it cannot be both at the same time. Okay? Cannot be both true and false at the same time. Sometimes we will have two statements that are connected by an and. When you're dealing with an and scenario, both the statements that make it up have to be true. So if you're saying P and Q, that is true when both P is true and Q is true. If both of them are false, or even if just one of them is false, the and statement as a whole is going to be false. So if you look in this table down here, which is called a truth table, we look at our and column. When P and Q are both true, that and statement is also true. The and statement is only true when both P and Q are true. The and statement is false in the other three scenarios. If just P is true, but Q is false, or the reverse of that, the and statement is false. And then, obviously, when both of them are false, the and statement is also false. The or statement is more forgiving. With the or statement, only one of P or Q have to be true. So with the or statement, as long as at least one of them is true, the or statement is true. So the or statement is true in 3 of the 4 scenarios. The only time the or statement is false is when P and Q are both false. Neither of them are true, so the or statement is false there. In the other 3 scenarios, the or statement is true because at least one of P or Q is true. So that's what our truth statement or our truth table gives us. Now, there's one other truth table we're going to look at. It's for the if-then scenario. So in our if-then truth table, I've got a column here for P and a column for Q, and then our if-then column. Now, this one might be surprising. The first 2 rows, not so much. If P is true and Q is true, if P, then Q is also true. Fine. P is true, Q is false. If P, then Q is false. That should make sense to most people. The last 2 sometimes throw people for a loop. If the premise is false, our if-then is still going to be true. And sometimes that can be confusing. But basically, if our premise is false, it really doesn't matter what the second half of our statement says. So let me give you a for instance. If my statement said this, if the sky is green, then pigs fly. We say that this if-then as a whole is true. The sky is not green, the sky is blue. So basically the second part of that statement, it doesn't really matter. We say that that if-then is still true. Okay, even though it's a scenario that can never happen, the whole if-then statement we consider to be true. Okay, so that's something that can kind of throw people. We don't go real deep into logic. If this is something that kind of makes your head hurt a little bit, don't worry. We don't do a whole lot with logic here, but I did want to introduce you to a little bit of it. Now, what we're going to do is we're going to use logical reasoning and actually go through and do a proof. So we're going to prove a theorem. It says if n is any whole number, then n squared is either a multiple of 4 or one larger than a multiple of 4. So I'm going to walk you through a mathematical proof. If n is any whole number, that means that it's not going to be negative, it's not going to be a fraction. It's a whole number, okay? So 0, 1, 2, 3, 4, and on up, okay? Now, if it's a whole number, then n can be even or it can be odd. So let me make a note of that. What I'm going to do is I'm going to do this proof in two parts. I'm going to first consider if n is an even whole number, and then I'm going to consider if it's an odd whole number. If n is even, then we can write it a certain way. If n is even, then we can write n equals 2k, where k is also a whole number. So let me give you a for instance. Let's say we're looking at the number 6. 6 can be written as 2 times 3, where 3 is a whole number. That's all we're saying there. Then, n squared is going to equal 2k quantity squared, which is 4k squared, because 2 squared is 4. And 4k squared is a multiple of 4. So now we've done half of the proof. The second half of the proof, if n is odd. If n is odd, then we can write n as 2k plus 1, where k is a whole number. So if k is 3, 2 times 3 plus 1, we get 7. Okay, so this is going to give me my odd numbers. Then n squared is going to equal 2k plus 1 quantity squared. So that's 2k plus 1 times 2k plus 1. So if you remember back to your algebra days, we're going to FOIL this. 2k times 2k is 4k squared. 2k times 1 is 2k. 1 times 2k is 2k. And then 1 times 1 is 1. So we have 4k squared. In the middle, we can combine to get 4k plus 1. And we can write this as 4 times k squared plus k plus 1. So notice this first part is a multiple of 4. Because it's literally 4 times something plus 1. So this is 1 larger than a multiple of 4. And then that concludes the proof. N is either even or odd. There is not another category. We've considered if n is even. We've considered if n is odd. We've shown that it's either a multiple of 4, n squared, or one larger than a multiple of 4. We have proven this theorem.